All right, let's talk about some the big O notation to understand the time complexity of cryptanalysis attacks. So let's start with the big O notation. So big O notation represents efficiency of an algorithm, time factor of an algorithm, space complexity of an algorithm, and so on. So it is represented by On, where n is the number of operations. Note that big O notation disregards constants. For example, if an algorithm requires c times n cube steps, where c is just an integer, or it doesn't have to be actually an integer, maybe a rational number, we write O(n) cube instead of O(c(n) cube because that constant actually doesn't affect much in the long run if you think about n as a very large number. Okay, so let's look at some of the basic examples. Let's look at the constant time algorithms O1. So here is a very simple programming code. So this is a function, print function, takes the input t and then array and prints the t value of that array on the screen. So this is just a one operation. This is why we call it O1. It is in constant time, regardless of your array size, by the way. So you can directly access an element in an array. Thus, regardless of the array size, this is a constant time algorithm, O1. Now let's look at it in polynomial time. My input to the function is the same. One of my inputs is an array of values, integers, and I also input an integer t. But this time, instead of printing the t value in the array, I am printing every value starting from 0 to t. So I actually print t values inside this for loop. So an array of 100 elements will take twice as much time compared to an array of 50 elements, right? Thus, complexity increases proportionally. This is why we call it polynomial time, or On. So there's a linear increase here. We can have On square. This is still polynomial time, but there's square, so it's just, it takes longer time to run this one compared to this one. So sorting algorithms like bubble sort and quick sort are of On square. So n is the number of elements you are going to sort, by the way. So a good tip is that average complexity of bubble sort is also On square. However, average complexity of quick sort is On log n. So this means that in practice, most of the time, quick sort will give you a faster answer, faster sorting compared to bubble sort. So in theory, they are in the same category, On square. And I really observed this in practice. I was trying to sort 32 gigabytes of hash values. And with the bubble sort, after 1 hour, it was still going, but I switched back to quick sort and I obtained the result in 14 minutes. So this is actually a nice tip you should use. But an algorithm actually might be longer to run, like n factorial, which is a huge number when n increases, of course. So a traveling salesman problem is an example to this. Given an input matrix of distances between n cities, the problem is to determine if there is a route visiting all cities with total distance less than k. So this is one way of stating the problem, of course. So this decision version of the traveling salesman problem is in NP. So this is for non-deterministic polynomial time. So it is a very hard question. So it takes very long time to solve it when n is really large. Okay. So if we try to plot it, as you can see, constant time algorithms or log n algorithms are really fast, and actually a binary search algorithm is log n. This is why we can search sorted values in a very fast way. But also, as you can see, On is fast. It increases linearly, but n log n is here, n square is here. As you can see, now it becomes concave, and others require a lot of time. This part is the increase in n, as you can see. And n increases. We can still perform these algorithms in a very fast way, but these becomes unreachable after very short amount of time. So let's define these algorithms. I already mentioned polynomial time. So an algorithm to perform a computation is said to be polynomial time algorithm if there exists an integer d such that the number of bit operations required to perform the algorithm with k bit input is O k to the power d. So d is just an integer, but of course it can be a rational number too. Exponential time algorithms. An exponential time algorithm has an estimate of O e to the ck, where k is the total input length and c a constant. Of course, I put e as the Euler's constant, but e, you can replace e with 2 or 3, and also in some algorithms you will see 2 to the something. And think about our brute force attacks, we require 2 to the k operations, which is exponential time. So this is why brute force attacks are not fast and we have security. And another question is that, okay, polynomial time algorithms run fast, exponential time algorithms runs really slow. Can there be anything between? And the answer is yes, and it is used in actually RSA when we perform factorization. So let's look at the factorization problem as the, let's first look at the trial division, the easiest method to factor. So the problem is finding a non-trivial factor of an odd integer n by trial division. So idea is as follows: you have an odd integer n. What you do is as follows: try all integers in the range starting from 3, 5, 7, and it goes until square root of n, and check if one of them divides n. Because you don't need to try, even values, because this is already an odd value, right? An even number cannot divide an odd number. So let's say that n is k-bit value, so log to n is k. So how many trials we should do? So we need to perform around square root of n divided by 2, actually, but in the big O notation we will get rid of constant. So we need to actually try around square root of n many values. So I said that n is k-bit, so we need 2 to the k over 2 many trials. And division of a k-bit integer with a k over 2-bit integer is of big O notation k square. In this, you have to believe me, but you can also check in a book about this. So a division requires this many operation. We have to perform this many divisions. So this trial by error actually requires big O notation 2 to the k over 2 times k square. As you can see, it is exponential time. So of course, this is the first method that comes to mind to factorize something. So question is, can we do better than that? And actually, yes, you can. And this is why we can break RSA when the key size is short, when the this n number that we are trying to factorize in RSA, which is actually the multiplication of 2 primes p and q. And nowadays we force RSA this number to be 3072-bit number, because there is a faster algorithm than this exponential time algorithm. But that algorithm is not polynomial time. If it were polynomial time, we would get rid of RSA and no longer use it. But it is sub-exponential time. So somewhere between polynomial and exponential time. So the definition looks a little bit strange, but we define a sub-exponential time algorithm as this, where it is still exponential, but there is a gamma value here, and gamma is between 0 and 1. Okay, so if k is the input size of an algorithm, and if the estimate of the time cost of the algorithm is this L gamma c, gamma between 0 and 1, the algorithm is called a sub-exponential time algorithm. So here one thing to notice is that if gamma is 1, this becomes 1 minus 1, 0, so you cancel this part, it ends up with e to the power ck, so it is exponential time. If gamma is 0, now that you get rid of this part, you end up with ln k to the c, but e to the ln just cancels each other, you end up with k to the c, so you end up with a polynomial time algorithm. So smaller gamma, which is close to 0, means your algorithm is faster, but when it is closer to 1, it is slower. So there's a sub-exponential time algorithm to factorize, so this is why we can RSA secret keys had to be 3000 bits and so on at least, where when we use elliptic curves, we can use secret keys like 256 bits. That is why we have this. So in the cryptanalysis part, for the public key encryption algorithms, your aim is to find this kind of algorithms, okay? So also let's look at the types of problems. I already talked about a little bit about decision problem when I talk about the traveling salesman problem. A decision problem is a problem whose solution or the output is just yes or no. This is why we call it a decision. So in the traveling salesman problem, we were asking yes or no question. Could you do it or not? Could you travel all of these cities with distance less than k or something? But the search problem is more complex because in this case, the solution is more than yes or no. You also provide the solution. For instance, in the traveling salesman problem, instead of saying that yes, you can, you also show which path you can follow and solve the problem. So search problems are, as you can guess, harder than decision problems, but this is sometimes counterintuitive because think about it in factorization. So I give you a number n and I ask you to factorize it. This is a search problem, but I can also give you that number and ask you if it is prime. So people think that these problems are identical, but actually you can still answer this question without factorizing it. So this decision problem is, easier than the search problem. This is why actually we can use RSA, because we can check if a number is prime or not. All right, so last definitions, Monte Carlo algorithms and Las Vegas algorithms. This might be useful when you design algorithms. So this is why I wanted to give these definitions. A yes-biased Monte Carlo algorithm is a randomized algorithm for a decision problem for which the yes answer is definitely correct and the no answer is incorrect with a probability at most epsilon. So when you have an algorithm and it says yes, it is definitely correct. But if answer is no, then it is correct with some probability. And actually, we use Monte Carlo algorithms to decide if a number is prime or not. Because in RSA algorithm, the algorithm starts with choosing two large prime numbers, okay? Since I cannot I randomly choose an odd integer and check if it is a prime number. Since the factorization is hard, I cannot factorize it. But with this kind of algorithms, I can be sure that it is prime and then, start using RSA. So it is important to have this kind of algorithms. There's also another type of algorithm called Las Vegas. A Las Vegas algorithm to answer a decision or search problem is an algorithm whose answer is definitely correct if it finishes, because sometimes it never finishes. But if it finishes, then the answer is correct. So in kind of search algorithms, Las Vegas algorithms sometimes, helpful to find a solution which is harder to find with other methods.